Okay, here we are. Section 3.2 from the book, roughly. Video 6, it is Wednesday the 24th. And hopefully I'm sitting in my apartment in San Francisco, safely returned from Texas. Right now it's Friday, I haven't left yet. Alright, so let's jump into this. Do a little recollection here. And from 3.1 what we did is we defined the derivative at a point x naught is x, and so here we go, f prime of x naught, which is a given number, turns out to be the limit as h approaches 0 of f of x naught plus h minus f of x naught over h. Well, sometimes you have to find multiple derivatives, like 10, and you don't want to have to take the limit 10 times and plug in a different x naught for each point. So what we do is we define the derivative as a function of f. So when we say the derivative of f of x, called f prime of x, is, here it is, it's the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is key, just to note that x is arbitrary. So basically you find the limit, it turns into its own function, which is clearly related to f. And then anytime you have a point that you want to find the derivative of, you just plug the point into the derivative, and you only have to do it. You only have to input. You don't have to keep taking the limit each time. So here's the example from video 5. Right? So we want to find f prime of x for the function f of x equals 4 minus x squared. On an example from the last video, we said what's the derivative at -1. And now I'm saying I want to know the derivatives everywhere, and if I wanted -1, I would just plug it in. So let's do that. We have the limit definition, writing all the steps out, and this becomes the limit. So here we go, 4 minus x plus h squared minus 4 minus x squared all over h. Doing our FOIL, this is x squared plus 2hx plus h squared minus 4 minus x squared all over h. And this becomes the limit as h approaches 0 of 4 minus x squared minus 2hx minus h squared minus 4 plus h squared, not forgetting to distribute the negative, which was the topic of algebra correct number 1. And hopefully, if you've done your algebra right, stuff cancels. Let's see here, what cancels? We got 4 and minus 4. We have minus x squared and positive x squared. Okay, those all canceled. So now we have 2hx minus h squared over h. Just like before, you're going to factor the h out. And cancel those h's. And continuing on with all this writing, plug 0 in for h and you get minus 2x. Oops, it's supposed to be a highlight. Okay, minus 2x. So now we see that. If f of x is 4 minus x squared, its derivative, f prime of x, is negative 2x. And now if I say, all right, I want to find the derivative of minus 1, 0, 1, 2, and 3, you don't have to take 5 limits, you just plug it in. So what's f prime of minus 1? Well, all you do is you take the derivative that we just found and evaluate it at x equals negative 1. And that bar is called an evaluation bar. We use it throughout Calc 1 and Calc 2. And this is minus 2 times minus 1. That's 2. If you wanted to find f prime of 3, it would be minus 2x evaluated at x equals 3. This is minus 2 times 3. And this is negative 6. So it's much more efficient once you find the derivative as a function of f instead of doing it for every point. Okay, so just a note on notation. All right. So if y equals f of x is a function in its graph, we can write the derivative many ways. If it's not confusing enough, these are all equal, okay? So f prime of x is my favorite. That's the way to write a derivative. You can also write it as just y prime. You can also write it as dy dx. You can also write it as df dx. And this actually comes from taking the derivative of x. So these are all equivalent statements. Now, I like to learn something, well, I like to learn all the time, but I didn't know this till, maybe I knew it and forgot, but when I reread it, I didn't realize that, I know how to use all these, obviously. And I know why this is called the differential form, and we'll talk about that much later. It's not that important, but this is the way Newton defined the derivative, and the differential was Leibniz. So it's not only differential, but it's historical. So just to be clear, so to look at that past example, the one we just looked at here, you could say f prime of x is minus 2x, or you could say dy dx is minus 2x, or you could say y prime is minus 2x. Okay. Now I'm going to throw in a guided practice problem. And this is probably going to take a little bit of time. So if you're actually going to go through with it, I'd give yourselves, I don't know, the way it's been working with these problems in class is like 5 to 10 minutes to work this out. But here it is. You want to find dy dx for the function y equals x over x minus 1. Okay. Not trivial, so that's why it should take 5 to 10 minutes. So I'll make a 1 second pause to allow you to turn the video off, do the work, and come back. All right. Hopefully that wasn't too bad. And as you'll see in a second, it's just an algebraic gymnastics thing. So let's get warmed up and do this. We have dy dx is f of x plus h minus f of x over h. I forgot to put my limit in there. The limit as h approaches 0. And here we go. F of x plus h, let me get my limit in there, is x plus h over s plus h minus 1 minus x over x minus 1. Now whenever I have these fraction ones, there's always the fraction with the fraction. Instead of writing big fraction bar over h, I put a little 1 over h out in front there to signify I'm dividing this whole thing by h. But this is just cleaner, and all you have to do is work on this piece, and then this guy here, this bit here, just follows along for the ride, because you know at the end you're going to cancel it. So, all right, well, it's fraction, so let's find a common denominator. And it's always just going to be the product of the denominators. Come on, pen. I broke my pencil. Okay, here we go. There it is. There's that 1 over h. All right, so up top here, I'm going to multiply by x minus 1. And then over here, I'm going to multiply it by x plus h minus 1. And this whole thing now lies over the common denominator. It's really important you understand what just happened there. Right? I found a common denominator, which was the product of these two, and basically cross-multiplied to get what's in the numerator. And here's where we all fall apart, because you have to make sure you FOIL and then distribute. So this first term is x squared plus hx plus x minus h minus, I'm sure I did that right, x squared hx x squared hx minus x, right? That should be, oops, what is this thing doing? That should be a minus. See that? See that? I almost got it wrong. So x squared minus hx minus x minus h. All right. So minus now x squared plus xh minus x all over this beast. Okay, that's the hardest step. Now we're going to combine. Let's strip away the parentheses first. So we have x squared plus hx minus x minus h minus x squared minus xh plus x, whoo, all over this. Okay. Wasn't going to take me 10 minutes. All right. Now for the destruction. X squared cancels with minus x squared. Hx cancels with minus hx. X cancels with minus x, and all that's left is negative h. So all that survived was minus h over s plus h minus 1 times x minus 1. And just as expected, these h's cancel. And we now have the limit as h approaches 0 of minus 1 over x plus h minus 1 times x minus 1. Now we take the limit and we get minus 1 over x minus 1 times x minus 1, which cleans up to minus 1 over x minus 1 squared. Quantity squared. Okay. Did you get that? If you did, you're a level 2 master of taking limits. All right. So that was a tough guy to practice. So there you go. Now we have all this power. Here's I'm going to save that for the finish. Okay. So here's a theorem that several people have taken calculus before in high school or even here at TMA, and I know on that last quiz there was a point where people weren't sure because they'd remembered things from the past. So here we go. Theorem. This is a theorem. If f of x has a derivative at some point x equals c, then f of x is continuous there. Okay. But the reverse isn't always true. So this is note. The reverse not always true. Case in point. Case in point, if you excuse me, if you let f of x be the absolute value function, this is not differentiable at x equals 0. Okay, but it is continuous. So if you graph it, you get this v here. So the point's there, so it's continuous there. But it's not differentiable. So continuity does not imply differentiability, but the reverse is true, and that's what this theorem says. And why doesn't it have a derivative there? Well, we'll talk about that in class, but basically, because it's a really sharp point, I didn't really do this picture justice, so. Let me try this again so I get a better picture. This is where a sketch works. So it's a really sharp point there, and if you're trying to find a tangent, how many are there? There's a bunch. There's that one, there's that one, there's that one, there's that one. There's infinitely many tangent lines to a really sharp point. To a curved point, here there's only one, right? It touches and goes away, and that's differentiable. So if you have a sharp point like the absolute value function, or as we'll see pretty soon, some functions have what's called a cusp. It looks like that. There's no derivative there, even though it's continuous. And so, yeah, that's that. All right, here's a guided practice to do when we get to class here in a minute. Find f prime of x for the square root function. All right, see you in a minute, hopefully, unless I'm stuck somewhere in the middle of America. on the side of the road waiting for a tow truck.